Welcome to our last summer series of CCDC virtual workshops. Today we're going to be exploring how to search and analyse metal organic structures, and it's fantastic to see so many of you online. So some housekeeping before we start. We are recording the session, but we will turn off the recording during the hands-on part, so you have the chance to ask us lots of questions. If you could mute yourselves during the presentation and the demo, that would be appreciated. If you have a question during the presentation or demo, then you can type these into the chat box at any time and we'll try and answer as many questions as possible. As usual for our virtual workshops, so we all get familiar with the chat box. We're going to navigate to the chat box now. So that's the little speech bubble. Open up the chat, and today we want you to tell us where you're joining from and what the view is like outside your window today. So I'll give you a few seconds to navigate to the chat box. Unfortunately, I'm joining from Cambridge, but I've had to close my curtains because it's far too sunny. So I can see some posts coming in. So while you're telling us about your views, for the hands-on part, you will need ConQuest and Mercury installed with an active CSD core license. You'll also need the workshop handout, which you should have received in an email on Monday. And after you've told us all a bit about yourselves, we'll also post the link in the chat box. If you don't have the CSD installed yet, there's not going to be time to install all our lovely software and data before the hands-on part, but you can still follow along to most of the session and try the hands-on part later. So after today, you will have learned some of our tips and tricks to search and analyse metal organic structures, and you'll hopefully know some new tactics in ConQuest. You'll be familiar with metal organic subsets in ConQuest, and you'll have learned how to export and analyse hit lists in Mercury. Over the next 90 minutes, during our Show One section, we'll give you an overview of relevant functionality in both ConQuest and Mercury, and we'll be giving a demo. It will then be your turn to try some hands-on examples before seeing some more advanced tips and tricks, and hopefully finishing with a fun quiz to test your newly learnt skills. So who are your tutors today? So I'm Susanna, and today I'm joined by Ilaria, Yinka, Seth, Eva, and I think we've got a few guest appearances as well, so Natalie's also joined. They'll all be on hand throughout the session to guide you and to help you explore the wonderful world of metal organic structures in the Cambridge Structural Database. All of our tutors today are from the Cambridge Crystallographic Data Centre, or CCDC for short. So CCDC is a non-profit organisation. It was set up to advance chemistry and crystallography for the public benefit. And one of the primary ways we do that is to curate and distribute the Cambridge Structural Database, or CSD for short. Alongside the database, we provide scientific software, enabling you to discover more from the data. We conduct cutting-edge collaborative research to help advance structural science, and we do education and outreach activities, and they're designed to help inspire and train the next generation of researchers. So that's a bit about us, but as well as knowing what your view's like outside today, we wanted to know a bit more about you. So you should hopefully in a second start to see a poll pop up. It may either pop up or be in the chat box, and we want you to tell us which of these you've done before. You can select all that are relevant, and once you've done that, click submit. So have you attended a workshop before? Have you searched the CSD? Have you visualized structures? Have you analyzed structures? Have you deposited structures with CCDC? And I can see the responses starting to come in. So it looks like a significant proportion of you have attended a workshop, searched the CSD and visualized crystal structures before, which is great. And a few of you have also deposited a structure with the CCDC. So while you're navigating your way to our poll and completing that, let's go back to the foundation of everything we'll look at today, and that's a crystallographic database. Crystallographic databases usually include publication details as well as crystallographic, chemical and experimental information. And importantly, they also include atomic coordinates, so we can really start to see the 3D chemical structure and explore the nature of crystals. And I think probably biased, but crystallographic databases and crystallographers are really special. There's an agreed file format that helps us share and understand structural data, and it's normal for crystallographers to make all of their data accessible. This means that every published structure is shared, and it has enabled curated databases to be established. The structures in these databases are processed and they're validated, so that enables you to learn from the wealth of data they contain as well. There are a number of different structural databases that exist, and here you can see 4 of them divided by content. The CSD contains every organic and metal organic structure, and alongside this database there's the Protein Data Bank containing macromolecular structures, the Inorganic Crystal Structure Database curated by Fitz-Karlsruhe, and the ICDD containing powder diffraction patterns. And that database includes patterns derived from data in the CSD as well. For today, we're going to be focusing on the CSD, but the other relevant databases to our metal organic research are probably the ICSD and ICDD, so you might see a bit more information about those popping up along the way. So if we look at the criteria for inclusion into the CSD in a bit more detail, then we can see the CSD contains single crystal and powder structures where coordinates have been refined. We can also find structures determined by X-ray, neutron or electron diffraction. Most structures, I think it's fair to say, contain a carbon or a carbon-hydrogen bond, but there are slightly more refined criteria, as we can see on the slide. And what happens if you are working in a crossover between one of the databases like the CSD and the ICSD? Well, back in 2017, a partnership was established between CCDC and Fitz-Karlsruhe, who curate the ICSD, and this led to the development of joint access and deposition services in 2018. This means that there is a common portal to deposit all organic, metal organic and inorganic structures, and our joint access structure service enables anyone to view and retrieve published deposited datasets associated with entries in either the CSD or the ICSD. If you want to learn more about this, we are hosting a joint workshop at the IUCR Congress meeting in August, and information about that is on our website. So we've now explored crystallographic databases, but let's zoom back into the CSD. So the CSD was established in 1965. It contains over 1.1 million structures and includes structures associated with scientific articles, patents, repositories, thesis publications, or published directly through the database as what we call a CSD communication. It's a certified core trust seal repository and is truly a community effort, with structures determined by crystallographers worldwide and every single CSD entry enriched and annotated by experts at CCDC. You can see the growth of the CSD since 1972 here, and one of our milestone structures. This is a copper paddle wheel structure, and it was the 800,000 structure added to the CSD back in 2015. So as we've mentioned, the CSD contains a mix of organic and metal organic structures, and we also have a split between single and multi-component complexes. Today, we are going to be focusing on the metal organic proportion of the resource, and that can be used in a variety of industries and helps us understand fundamental chemical bonding as well. If we look at some of the different chemistries in the CSD structures, we can see the rapid rise to fame of metal organic frameworks in the CSD on the left, and soon we'll see that starting to pop up. So we can see metallocene already in 1992, and we can start to see MOFs rising in dominance in the CSD. MOFs now account for around 10% of the database, and we can also dig a bit deeper and explore the metals in our MOF structures. So the animation on the right showed the metals, and we can see that copper dominates, but elements like silver, zinc and cobalt were on the rise, and lanthanides are starting to appear in the list too. So we have seen MOFs now account for about 10% of the CSD, but let's just rewind a bit and think about what a MOF is. So back in 2013, IUPAC recommended that a MOF is a coordination network with organic ligands containing potential voids. But a 2012 report noted that there's no clear consensus if MOFs should include 1D, 2D, or 3D networks. 25% of respondents believed MOFs must have proven porosity, and they noted that in fact there was no IUPAC definition for what organic means. Although conversation has progressed since then, and there are various task forces dedicated to defining this space, I think it's fair to say that there's still some debate in the community. So I wanted to finish our definition with a quote from the Commission on MOFs, and they said, finally, we should perhaps remind ourselves that what matters, or what should matter in the real world, are the properties of our materials, not what we choose to call them. And as Juliet says in Romeo and Juliet, a rose by any other name would smell as sweet. So before we look at how we might use metal organic structural data, let's look at some fun facts. So the first metal organic structure with coordinates was published in 1938 by Monteith Robertson, and the first MOF structure, according to our MOF subset, was published just two years later in 1940s. Since the early 1990s, metal organic structures have been outweighing organic structures, and they now account for around 57% of the resource. Over 40,000 different authors have contributed to the CSD MOF structures, and the most prolific author of MOFs is Pascal Dietzel, who has performed time-resolved synchrotron X-ray diffraction measurements, leading to many individual data collections, currently over 1,900. So what can we learn from metal organic structures in the CSD? They can help us explore metal coordinations. They can provide valuable insights into ligand coordination modes, metal coordination numbers, bond lengths, symmetry and shape, spin states, ligand cones, polynuclear complexes, magnetism, and they can also help provide software parameterization. So there really is a wealth of knowledge contained in the individual structures. They are relevant in helping to design new materials for a wide range of different industrial applications, such as energetic materials, ferroelectricity, magnetic materials, catalysts like the Grubb catalyst you can see here, or gas storage and separation. And they can also be useful in the pharmaceutical industry too. So now we have seen more about the CSD, it's again time to find out more about you. So this time we want to know what research areas you're using metal organics for. So you should hopefully start to see the chat poll pop up either in the chat or on your main window. And again, I think you can select all that are true and then press submit. I'm starting to see the responses. It looks like gas storage and separation is winning at the moment, with catalysis a close second. Looks like it's going to be a tight race though. So while you're filling that in, we are now going to look at what tools we can use to explore metal organic structures. And our show one part will be using CSD Core suite of software and data. In particular, we'll be showing how to visualize structures with Mercury, how to search for structures using ConQuest, and how to analyze our structures using a combination of ConQuest and Mercury. So we're going to start by looking at Mercury, which helps us understand how structures pack together, what 1D, 2D and 3D networks exist, and they help us to visualize important features, including things like voids or polyhedra display. So to open Mercury, we're going to be clicking on this icon or navigating to it in our start menu. Once opened, we'll see the Mercury interface, which should be already familiar to quite a few of you on the call. And you can see the structures listed by ref code or database identifier on the right-hand side. We're going to start our exploration by looking at ref code WUTXUH. So we're going to type that in the structure navigator, and that will allow us to jump to the structure. So that's WUTXUH. So we can see when we navigate to this structure that it's a polymer, and mercury displays polymeric bonds with alternating long and short lines, as you can see here. For metal organic structures, we may also decide we would prefer to visualize them using polyhedral representations with the metal organic coordination centers. So we can easily do this in Mercury by changing the style drop-down menu to polyhedra, or by navigating to the display menu, styles and polyhedra. And if we do it for our chosen structure, we can start to see the polyhedra. You can also see in our styles menu polyhedra settings, and we can start to change some of the settings about our polyhedra, including how transparent they are. And you can see a more beautiful example of a polyhedra display using this ref code. So how else could we explore our chosen structure? So since it's a polymer, we probably want to learn more about how the polymer is constructed. And to do that, we navigate to Edit, Polymer Expansion, and that allows us to expand the polymeric bonds. We then see our pop-up, and in our first example, we're going to select Expand by Subunit and click where we want to expand. So it will then start to expand the subunit, and you can continue your expansion. We can also expand by a whole unit, which in this case gives the same results as steps done on the two previous slides. So we've selected whole unit and we can see the same result. Or we could choose to expand all. With now more of the structure displayed, to help us identify where the polymeric bonds are, we could choose to tick the label on polymeric bonds. And these are now displayed with PO labels or polymeric labels. So each of the structures in the CSD has been edited and enhanced by editors at the CCDC to ensure they have the correct chemical connectivity. But if you're using your own structure, CIFs don't usually contain this information. So we would recommend going to Edit or to Edit Structure and using the Identify Polymeric Bonds functionality. And just to give you a reminder, if you are manipulating structures in Mercury, you can save your structure for later by going to File, Save As, and selecting the Mercury compressed option, or to save a high resolution image, you can use File and then POV-RAY. Our final tip for looking at metal organic structures is to explore voids. So we learned earlier that it's a common belief that MOFs must have proven porosity. So let's see how we can visualize voids in Mercury. To do this on our structure, we'd need to navigate to Display and Voids, and then we see the pop-up on the left of the slide. The pop-up provides some information about the void calculation. It allows us to change some of the settings, and we have different display options. So we can now visualize individual structures like this one. But how can we start learning from the collection? A good place to start is by searching the CSD. We have three main ways to do that. And today we're going to be focusing on ConQuest, our desktop search interface. So to open ConQuest, we use our magnify glass icon, and that opens ConQuest. And we'll see the ConQuest search interface with our different build query options or routes on the left. Once we construct a query, we'll then see our search setup window, and one of the filters that you can see at the bottom right and that we'll be using today is only organometallic. This restricts the search to structures containing at least one transition metal, lanthanide, actinide, or any elements on the slide. For metal organics, one of the first things we might want to search for is a metal with a particular oxidation state. Currently, oxidation states are captured in the compound name and are not a property of the atom, although we are evolving our underlying databases to enable us to change this in the future. This means to search for oxidation states, we recommend using the name, class, query type, and entering Roman numerals in lowercase surrounded by brackets. You could also precede that with the name of the metal if you wanted to narrow it down further. If we do that, we start to see the results in our View Results pane, and we can see the query highlighted. If we look at the compound name in more detail, we can see they include information about the polymeric nature of the structure, oxidation states, ligand names, and if appropriate, words like clathrate, hydrate, or sulfate. are also added. On the All Text pane, we can click to see the associated publication or the underlying deposited CIF file, and we can also navigate to see the curated chemical diagram. Or we could choose to see a 3D visualization of the structure, and left-clicking on each of the tabs on the left will display different information. Right-clicking on our 3D visualizer enables us to change the display style as we've seen before. For metal organic structures, you can also use the name class build query to search for metal organic polymers, as these should all have katina at the start of the name. If you're interested in multi-component structures or clathrates, then using the Z density query option on the left can be useful, and this can also help find more porous structures as well. Finally, in the CSD, when available, we also try to capture additional details about the compound, like magnetic, explosive, etc. And you will see a starting list of search terms in our all text window. After text numeric searches, the next thing we might want to do is search chemical contents. And we can either use formula or elements to do this. In formula, we can enter a formula, decide if other atoms are allowed in the structure or not, and also make our formula a bit more variable by clicking Select Table. In this instance, we could decide to change our ferrocene formula to search for any metallocenes, or to include ferrocenes with other substituents by changing the atom count. To search for metallocenes, we can click on Groups of Elements by clicking on the yellow boxes on our periodic table. Here you can see that element searches work in much the same way, and you can choose the count of elements by ranges, equals, greater than, less than, etc. Our final way of searching for metal organics is normally through the draw query. And at the end of your handout for today, you should have an overview of the basic features of the draw window. Parts particularly relevant for metal organics are changing the atom type, and you'll see you can select any metal, any transition metal, or you could select other elements to pop up the periodic table again. We may also need to change the bond type, and we'll see some examples of that later. And you can right-click on an atom to change some of the atom properties. And for metal organics, things like the number of bonded atoms are going to be useful. So we could select how many times our metal is bonded. When it comes to searching for metal organics, it's useful to know some of the CSD conventions. So when appropriate in the CSD, we use a range of different bond types, including aromatic, delocalized, pi, and polymeric. And you'll see an example of a structure with some of these bond types on the top right. Our 2D representations also include missing hydrogen atoms, squeezed or masked areas, and charge is only added for charge balance purposes. This means when you start searching using, it's often useful to use any bond. It can help find more complicated structures such as polymers, delocalized and pi bonded systems, and you can then filter your search after then. So here's 3 different ways you could search for a copper surrounded by 4 oxygens, and what new types of structures these different approaches will find. So we saw earlier that the 800,000 structure in the CSD was a copper paddle wheel, and we could also use the draw query to help us understand the nature of these types of structures and how they change if different metals are used. To do this, we can navigate to the 800 structure by typing in the ref code, and then use this structure to start our query by using as query. We could then edit the structure and erase parts of it so the query is more general. And this time we're going to click on Add 3D, select the parts of the structure we're interested in, define the parameters and to analyze. And this time I'm going to look at something simple, just like the copper-copper distance, and then we can perform a search. We can then view our results, and again, our query is highlighted, and once the search is complete, we can decide to analyze hit list and go to analyze data. If we include defined parameters, that will allow us to see the parameter displayed in our Mercury window that pops up, so we can see it on the individual structure. And it also opens our data analysis window, where we can start to learn about trends in structures in the CSD using things like plots. So before we move to the demo, the final thing we wanted to tell you about is subsets. So we've seen that it can be relatively complicated to search for metal organic structures. So to help you find some of the most complex of these types of structures, we've created 2 targeted subsets of metal organic frameworks. In this work, Aurelia, our sponsored PhD student, looked at well-known MOF structures and what type of linkers were contained in these structures. She then constructed searches for these structures in ConQuest and kept adding and adapting the searches to cover all of the recognised MOFs. So this led to combining 7 different search queries and transforming these queries for use in our CSD Python API. There are now 2 MOF subsets available to use in ConQuest, and you can either view these directly by going to View Databases, or you can select subset to filter your results to a predefined hit list in the Search Setup tab. So select subset and then entries in a predefined hit list. Our MOF subset is also available through our CSD Python API, and that allows programmatic access and also enables you to change the definition of a MOF if you want to change the script. So our MOF subset script is a starting point. It's purposefully broad so you can filter down, since we saw earlier that there may be some disagreement as to what a MOF definition is. So I'm now going to pass over to Yinka, who's going to show us in more detail through a demo.
Okay, great. So I will be going over a couple of searches first in ConQuest, and then we're going to view the data analysis module in Mercury. So in ConQuest, I'm going to be showing you how to search within the MOF subset, how to conduct a search that you can use the only organometallics filter on, and also how to add 3D parameters that can then be exported into Mercury. So the first thing I'm going to show you is how to search for a specific element and just limiting it to the MUF subset. So let's say, for example, you're interested in looking at structures in the MUF subset that has uranium. You can either type the symbol in here if you know what you're looking for, or you can also bring up the entire periodic table by clicking on Select from Table. And I'm going to select uranium and done. And that should now be in the box. And this is the only search definition that I'm going to construct. I'm going to click search, and here is where we can now select our MOF subset. So in the search setup window, I will take 3D coordinates determined and then select subset. As Susanna showed in the presentation, this brings up the restrict search window, and I will click on entries in a predefined hit list, and this should bring up all of the predefined subsets. And I'm going to scroll down to MUF subset. This is a large subset, so it's going to take a little bit to load. While it's loading, I'm going to point out that if we had conducted a search previously in this ConQuest session, entries in the hit list loaded this session would be an option to us. If you have a SIGSRF file, or if you've conducted a hit list combination, that's an option that you will be able to select here. So now that our MUF subset is loaded, you see some information here on when the specific ref codes were added to the CSD. I'm going to click OK. And now back in our search setup window, you would see that search is restricted to this ref codes, and that is the MOF subset, and you can start search. Before that, we could select only organometallic here, but since we are looking for uranium, it will naturally return only organometallic structures. So as we click start search, you will start to see your results populate on the right hand side, and you can scroll through the results to see where uranium is. While the 2D diagram is useful, I quite like looking at the 3D visualizer instead, because you can then manipulate and get a better view of the structures. A couple of things that I like to do in the 3D viewer is first to change the display style of the molecule. So you can right click here and click display style, and I prefer capsticks. So again, you just get a different view of the structure. And also something that is useful to do is click on, again, right click in the 3D visualizer, click on settings and show circles for aromatics so you can see the display for aromatic um, bonds. And so again, you can just sort of scroll through and view the different structures that have uranium. You could also label your atom if you are interested, and there are options here that you can use. So that is just one way to search within the MUF subset. But what if you are interested in other metal organic structures? I'm going to go back to the Build Queries tab, and what I'm going to do is sketch an organic structure, but I'm interested in returning metal organic structures. So I'm going to click on Draw, and that should bring us to the Draw window. I like using the templates here because it's just a little bit easier and you don't have to worry about angles and bond distances. So I've selected an aromatic five-membered ring. I'm going to replace one of the carbon atoms with a nitrogen, and that is all I'm going to do in this sketch. So here is where we can include our only organometallics filter. So this will return any structure in the entire database that has this ligand in it. So we could choose to clear a subset here so that we're not searching the metal organic framework subset, but we might be interested in using it later. So I'm just going to untick it here. And now we are searching the whole CSD, and we can start our search. And again, we should start to see structures pop up in our hit list window. You will see highlighted in red what matches our substructure that we defined. So again, as we start to click through this, you see the highlighted match. So we got about 861 hits back, and I'm going to go to the 3D visualizer. So as you can see in the diagram, you have this ytterbium atom interacting with the five-membered ring, but in the 3D visualizer, you can get a better view of what the interaction actually looks like. So now if you look at this interaction and you go, oh, I actually want to further explore this type of metal and ring interaction, it's probably a little tough to sketch this interaction yourself. So what you could do is use one of the results that you got in your search and use that as a query. So I'm going to go back to the diagram, and this is the structure that I'm going to use as my query. So there is this uses query option in the bottom right. If we had multi-components in our structures, we would have an option to make each chemical unit a separate query. But since this is all just one unit, the only option we have is the biggest chemical unit only, and I'm going to click OK. This will bring us to the Build Queries tab, and if we were interested in this structure specifically, we would just use it as a query. But I'm going to edit it for a couple of reasons. First off, I want to remove this other group on the structure. So I clicked Erase and clicked on each atom that I want to remove. I also want to expand this search a little bit more. So I'm interested in more than zirconium. So the first thing I'm going to do is click More and Other Elements. And I want to see every first-row transition metal that has this sort of interaction in the database. So I'm going to click 1R, and all the elements selected will be highlighted in green. Click OK, and I can just click on zirconium, and that is now replaced with 1R, meaning that any first-row transition metal with this interaction would be returned. I also want to replace this group with any substituent groups. So I'm going to click on any in the bottom of the draw window. And when this is highlighted in red, I can just click to replace that. So this is what we're going to search, but before we do that, I'm going to add some 3D parameters so that we can export our results in Mercury and conduct further data analysis on this. So to add 3D parameters, we're going to click here, add 3D, and that will bring up the geometric parameters window. So a couple of things I'm going to point out here. As you click on an atom in your sketch substructure, the valid parameter options will start to come up. So I've clicked on one carbon, and the options are atomic properties. If you click define, you can then see your options for what atomic properties you can include. And as you define parameters, they will start to show up in the 3D parameters window. If you clicked on two atoms, then you get a distance option, and then you can start to also define some objects. If you clicked on three atoms, you get an angle option. Four, you get torsion. And if you select a whole ring, you can define a centroid or a plane. And there are also other parameters you can define. So some of the parameters that I'm interested in this substructure is I want to see how the distance between the metal center and the five-membered ring changes. But since the type of interaction we are looking at is a five-coordinate interaction, the best way is to find the geometric center of this five-membered ring by defining a centroid. So as all these atoms are highlighted in blue, that means that I can define a centroid, and that is now available in our defined object. So now we can start to define our distances and angles. So the first thing I want to define is the metal and centroid distance. And so as you can see, the distance is now highlighted in green, and you can click define, and that would define distance one. So distance one might be confusing, or you might not remember what it was if you're defining multiple distances. So an option is to actually rename your defined parameters. So I'm going to rename this as a centroid metal. You do have a limit of 6 characters to what you can define, and it must start with a letter. If you also wanted to limit the range of the distance, you can add that here, and that would only return structures that fit that limit. And I'm going to click OK here, and so now you see the centroid metal distance is defined here. Another thing I want to include is the distance between the substituent group and the metal center. So I'm going to click those and click define. And again, I'm going to change this to an X metal to know what that distance is, and click OK. And then finally, I want to see how the angle between the substituent group, the metal, and the centroid changes based on what the substituent group is or the metal center. So I click into section the X group, 1R, and the centroid, and I'm going to define an angle. I'm going to keep it as angle 1 because that is the only angle property that I am defining. And once I'm done here, I can click done, and you can see the 3 parameters that we have defined here. And now we can start our search. I usually say no to override an existing query, just so that I can always go back to this initial query if I want to edit it. And so now we're back in our search setup window. I'm going to leave only organometallics, even though, again, we've defined this as a first-row transition metal, so we should only return organometallic structures. And again, we're searching the entire CSG, and we have our 3D coordinates determined selected. So I'm going to click Start Search, and our results should start to populate here. And again, you see our matched substructure. You can see the parameters that we've defined. They're going to be in the top right corner. And so as you click, you can start to see the different parameters. But another way to view the parameters is to go to the 3D visualizer window, and you have some options here. So first off, it would default to showing all the parameters at once. So you can click through with the arrows to change what you want to see. So you can see the centroid metal distance, and again, as you click through your results, you can view the distances, you can view the X group and metal distance. They will be superimposed here, and also your angles would be viewed here. So now that we have our 3D parameters defined, how can we gain more insight into what is actually going on here. So you can click Analyze Hit List and Analyze Data, and that's going to bring up the Analyze in Mercury window. Before I move on to the Mercury option, are there any questions in the chat box that about ConQuest?
I think you're all good for now.
Okay, great. The included parameters would, the defined parameters would be included by default here. But if there are other parameters that you're interested in, such as z-value, cell data, you can also select those here. And once you are ready, you click Analyze in Mercury, and this will export the structures and should load Mercury. This will open both the main Mercury window and the data analysis window. Sometimes the data analysis window is a little bit hidden behind, but I have adjusted my windows so you can sort of see them side by side. So the first thing I want to point out here is when the data analysis window opens, you also have this hit fragment display options. So what you can do here is if you only want to show your substructure match, you can do that here, or you can untick. You can change this from a tree view, but I'm going to leave the defaults here and just close this window. So let's focus now on the data analysis window and get a little bit more familiar with what we're actually looking at. The structures are arranged by identifier, which is the search number, the ref code, and the number of fragment hits within each structure. The name is the ref code. We also have query, which is which query was used to generate this result. The fragment is, again, which part of the fragment of the structure we're looking at. We have our angle one, we have our centroid metal distance, and we have the X group and metal distance. So the first thing I want to do here is plot an histogram of the angles just to see if there are any visible clusters or trends. So I will just left click on this header, which is angle 1, and then click on plots and histogram. And that should bring up the histogram view. So we can see that there is a cluster of angles here, but then we also have a group that is somewhat of an outlier over here. So when you click on a bar in a histogram, it's going to highlight the corresponding structures. But since these are not sorted by angle, they're sorted by identifier, it might be a little bit hard to look at. So what you can do is right click on the angle header and click sort. And now you see that the group that fits in this bar is now highlighted. So you can start to click through and that would place the structure in the Mercury display window. What could be helpful here is to see the label of which metal centers are in this structure. So we can see that the structure has a chromium with some carbon group on it. And we can look at this one. This is a titanium bounded to some nitrogen groups. And again, this is chromium and chromium. So those are the structures that fit in here. So we can also click on this other bar and scroll to the highlighted section and page through and try to start to see if there is a trend. Again, this is titanium group, so it's not really clear why there are some angles with titanium over here, and then there's also this outlier. So what you could actually do is go back into ConQuest and replace that any first row transition metal with titanium and try to get better information on what the different substituent group is, how they're affecting your angles. So some of the other type of plot we can generate is to see if there's any correlation between the X metal distance and how the angle changes. So if you select the two groups and go back to plot, you should now you can click on scatter plot, and that should give you an option of you should start to see the scatter plot. And you can see highlighted in red here, that's the structure that's currently in the window. So our scatter plot, there really isn't much of a correlation, but we can see that it's also similar to our histogram. So you can start to click on each individual point here if you wanted to see what the outliers are, and get again some feel for what is going on here. So the trend I'm sort of seeing here is that our first row transition metals, the early metals, depending on what the substituent X group is, you will either have a cluster around 100 degrees to roughly 130 degrees. There are some around 180 degrees, but based on which metal, and you can get a little bit more specific on your ligands. So if you're looking at carbonyl groups, or if you're looking at other type of for example, there are some groups here that are like borides. So you can use that to further refine your search in Mercury. Some other things that I want to point out here is if you wanted to get some descriptive statistics on on the parameters you have exported to Mercury, you can click on statistics and descriptive statistics, and that is going to show you a couple of things like your maximum angle, your minimum angle, the sum, and mean. And this will be done for every parameter that you've defined. Another thing that I would like to point out in the data analysis window is if you go to tools and calculator, you can then calculate specific things. So for example, if you wanted to see specifically just the standard deviation for angle 1, so you'd click on standard deviation angle 1, you do have to give a name here. So I'm just going to say SD standard deviation angle 1, and then click calculate, and that will bring up the results, so you can see that here. And so this is just a very brief introduction into how to use the data analysis function in Mercury using results from your ConQuest search. I definitely recommend exploring more on the different menus here to see what else you can do. And with that, I will take any questions.
So our next part is going to be recorded. And thanks, Anna, for starting the recording. And it's our Explore More. There's not enough time to explore all the ways that you can search, visualize, and analyze metal organic structures. But over the next few minutes, we will show you a few more tips and tricks, and we will journey through the collection. Our first journey is going to involve exploring chemical concepts that we learnt during our studies and how we can observe these concepts using structural data. So one effect we have probably all heard of is the Antella effect, and although I vaguely remember the lecture, I don't still have my undergrad notes, but according to Wikipedia, the Antella effect is most often encountered in octahedral complexes of the transition metals, and it's very common in 6-coordinate copper-2 complexes. So we could decide to look at an individual structure to see this, and here I've navigated to a 6-coordinate copper surrounded by nitrogens in the CSD, ref code XUTYOA, and I've measured the metal nitrogen distances by changing the picking mode. But the beauty of the Cambridge Structure Database is that we can also learn from the collection of structures as well as the individual structures. So what we could do is construct a draw query, and this is an animation, and add a copper atom, limit it to 6 coordinate, and then define, in this case, our copper oxygen distance. If we use the periodic table, add our copper, then add an oxygen, and then right click and change the number of bonded atoms to 6. And then we're going to add a 3D parameter like we saw earlier. And we're going to define the distance. So once we've done that, it will appear in our 3D parameters, and we can click search. We can then decide what filters to use, and then proceed with our search. So once we do this, we see the results, and once again, we can analyze our hit list using analyze data, and we can include our defined parameters like we saw earlier. So include defined parameters. And then we get to see our data analysis window, and we can start to create plots to see the trends in the data. So a simple plot, like we saw before, is a histogram, and we can see 2 peaks on our histogram. We could refine and evolve this method to see what other metal atoms exhibit Jantella distortions, or we could see how the distortions change with other types of ligands. So we saw earlier that we can use data in the CSD to help define new materials such as catalysts, but how would we go about finding catalysts in the CSD? So we could decide to pick a relevant journal, something like Organometallics, where we know this information or is published, or we could try a text search. So we could combine catalyst or catalysis, all text searches, and see what results we find. And then perhaps we could go on to do a similarity search on the results using either WebCSD functionality or through our Python API. Or alternatively, we could look at some of the more well-known catalysts and start to construct some searches using the draw query. So some of the types of structures known to exhibit catalysis have been explored here, like metallocenes, palladium structures, grubs, catalysts. And if you want to know more about catalysts in the CSD, we have a dedicated blog. The link is on the bottom of this slide, but should also be included in your links, in your notes handout, if you want to see more about that. Our final tip for today's session is centered on high throughput analysis. So we know aspects of MOF research are well suited to high throughput analysis, and researchers often look at things like topology, pore size, void space, and surface area. So, and that's why we've recently launched, so earlier this year, our CSD MOF collection. This complements our CSD MOF subsets that are embedded into the CSD portfolio. And you can see here a CSD entry in our CSD MOF subset, and then a corresponding entry in our MOF collection. The MOF collection provides a good starting point for high throughput analysis. It includes over 10,000 3D porous MOFs, with all 3D MOFs containing over 10% void space. To aid high throughput analysis, each MOF is converted to space group P1, non-bonded solvents are removed, and missing hydrogen atoms have already been added. So the CSD MOF collection is provided as a collection of CIFs, and it also contains reference spreadsheets to enable further categorization within the collection. It's free and open. It has a Creative Commons license, and you can find out more or download the collection from our website just by going to our homepage, community, CSD community, and then CSD MOF collection.